Okay, picture this. Imagine you're tasked with mapping out a sprawling, incredibly complex city. You need to know exactly where every single building is, the distance between every street, the exact layout of every neighborhood, but there's a major catch. You are completely blindfolded. You literally can't see a single thing. So, how would you figure out where everything lives? Well, this is exactly the core problem scientists faced when they first tried to understand the atomic structure of crystals. I mean, how do we figure out the precise three-dimensional location of every single atom in a solid piece of material when those atoms are far, far too small for the human eye or even a traditional microscope to ever actually see?
Welcome to The Explainer. Today, we are tackling Theme 2 of our series, the reciprocal lattice and X-ray diffraction. We're going to demystify exactly how we uncover the hidden architecture of the physical world. It's an incredible scientific journey that takes us from physical crystals you can literally hold in your hand, all the way to a mind-bending, inside-out mathematical trick that scientists use to see the completely unseeable. Okay, let's quickly look at our roadmap for today. We'll start with 1, the invisible architecture of crystals, then move to 2, the direct lattice. After that, it's 3, X-ray diffraction, 4, the reciprocal lattice, and finally 5, why this mapping matters. All right, kicking things off with sections 1 and 2, the invisible architecture and the direct lattice. Let's start with physical space, the tangible reality of how atoms actually arrange themselves before we even try to measure them. You know, a crystal isn't just some random jumble of atoms. It is a perfectly repeating, highly ordered physical grid. Think of it kind of like 3D wallpaper. This concept was actually first formalized way back in the 19th century by a French naval officer named Auguste Brevet. He realized that any crystal can be described as a 3D network of nodes, which we now call a Brevet's lattice. By just using 3 fundamental directional vectors, A, B, and C, you can map the physical jump from one atom to the exact next identical atom in that repeating pattern. This right here is what we call the direct lattice. It's the literal physical space where the atoms actually live. And this brilliantly illustrates how nature essentially plays Tetris. In these lattices, atoms act pretty much like hard spheres, just trying to pack themselves together. It's exactly like stacking oranges at the grocery store. You could stack them directly on top of one another, which, if you think about it, leaves a whole lot of empty space. We call that non-compact or simple cubic packing. Or you can nestle the next layer of oranges right into the little dips and hollows of the layer below, which creates a really compact packing, like a face-centered cubic structure. And here's the cool part. When atoms pack together like this, they create very specific geometric gaps or interstitial sites. If a gap is surrounded by 4 atoms, it's a tetrahedral site. Surrounded by 6, that's an octahedral site. This hidden geometry dictates exactly where smaller ions can sneak in and fit, all based on their ionic radii. Moving right along to section 3, X-ray diffraction. So, we know these atoms are meticulously arranged, but we still have that original problem, right? They're infinitely smaller than the wavelength of visible light. We can't just shine a flashlight on them. We need a totally new tool. Which brings up a really fascinating question. If the atoms are physically spaced out, and we literally cannot see them, what does our measurement tool actually interact with? Well, the answer lies in X-rays. X-rays happen to have wavelengths that are roughly the exact same size as the physical distance between atoms in a crystal. So instead of acting like a camera taking a photograph, our X-ray acts a lot more like a specialized wave that bounces off these atomic layers. So how does that bouncing actually work? It's governed by this beautiful piece of physics called Bragg's law. Step 1. An X-ray beam hits the plane of atoms at a very specific angle, theta. Step 2. Because those atoms act as solid obstacles, the X-ray wave diffracts, or scatters off them. And then, step 3 is where the magic happens. Normally, all these scattered waves would just cancel each other out in a chaotic mess. But at certain perfectly aligned angles, the peaks of the waves align beautifully with other peaks. This is what we call constructive interference. When that happens, the math perfectly aligns. 2 times the physical distance A multiplied by the sine of the angle equals an integer multiple of the X-ray's wavelength. Boom! When we get that strong signal, we can work backward to calculate the exact physical gap between the atoms. Which brings us to section 4. The reciprocal lattice. And here is where the story takes a bit of a wild turn. Looking at a massive, complex web of scattered X-ray angles is incredibly difficult to map back to a physical 3D grid. To interpret this X-ray data easily, scientists realized they had to literally flip their map inside out. Think about it like this. Imagine trying to understand a wildly complex symphony just by looking at the physical sound waves jumbled on a screen. That's the direct lattice. It's the raw physical reality. It's like just listening to the audio. The reciprocal lattice, on the other hand, is like reading the sheet music. It is a completely different way to represent the exact same symphony, but it's organized by frequencies and harmonies instead of raw sound. The reciprocal lattice is a purely mathematical space perfectly tailored to map the frequencies and diffraction angles of those X-rays we just talked about.
Now, what's really interesting here is how these two spaces perfectly mirror each other. In the direct lattice, our real space, our vectors A, B, and C measure physical distance in meters. Easy enough. But in the reciprocal lattice, which is often called K-space, we use vectors A star and B star. These don't measure distance at all. They measure wave vectors, which is actually 1/meters. Look at the math. A star equals 2 pi divided by A. This means they are completely inversely related. So if you have a really large physical distance between atoms in the real crystal, it shows up as a tiny vector in the reciprocal lattice. By flipping the physical world into K-space, all those messy, complex X-ray diffraction patterns suddenly plot out as a neat, highly readable grid of dots.
Now let's see how this builds into something even more profound when we start looking at how electricity moves. Let me read you a quote directly from our source material. Electronic waves can be diffracted or reflected when the Bragg condition is satisfied. The nearly free electron becomes a discontinuous curve. You see, in a crystal, electrons aren't just little solid balls zipping around. They actually behave as waves, just like the X-rays. And because they are waves, as they travel through that crystal's atomic grid, they also experience diffraction. When an electron's energy hits a specific frequency that perfectly satisfies Bragg's law, it actually gets reflected back by the lattice itself. Its energy curve literally breaks and becomes discontinuous. And this invisible point of reflection creates a strict, hard boundary. We map this boundary in our reciprocal sheet music as something called the Brillouin zone. The Brillouin zone is basically the fundamental volume in reciprocal space, specifically the area between minus pi over A and plus pi over A. It acts as the ultimate invisible electric fence. It dictates exactly how much energy and what wavelengths an electron is allowed to have before the crystal lattice just bounces it right back. Honestly, understanding the Brillouin zone is the absolute key to understanding energy bands in any solid.
All right, wrapping things up with Section 5, why this mapping matters. We've gone from physical atoms to X-rays to a totally abstract inside-out mathematical universe called K-space. You might be sitting there wondering, does this highly theoretical concept actually impact my daily life in any way? The answer is a massive, resounding yes.
Because of those Brillouin zones in the orbital overlaps we just mapped in reciprocal space, scientists can perfectly predict the physical properties of materials. For example, there's this groundbreaking classification by physicist J.B. Goodenough. He defined a critical intercatonic distance, which he called RC. If we look at titanium oxide, the atoms are packed tighter than RC. The electron waves overlap beautifully, making it a great metallic conductor. Vanadium oxide sits right on the edge, so it acts as an insulator at low temperatures. But nickel oxide, its atomic spacing is significantly greater than RC. The electron waves are totally trapped by those Brillouin zone boundaries we just discussed. They just can't flow, meaning nickel oxide is a strict insulator.
So the crucial point to take away from all this is simple. This bizarre, inside-out mathematical map is absolutely not just an academic exercise. By understanding and mapping the invisible frequencies of K-space, we unlocked the power to engineer exactly how electrons behave. It is literally the absolute foundation of all modern solid-state electronics. Without the reciprocal lattice, we wouldn't have semiconductors, we wouldn't have computers, flat screens, or the smartphone sitting in your pocket right now.
It is just incredible to think that by mapping an invisible city, we essentially built the modern world. Which leaves me with a final thought for you to ponder today. If the completely invisible math of K-space perfectly dictates the physical technology you are using to watch or listen to this exact explainer right now, what other hidden, abstract dimensions are out there silently shaping the reality we interact with every single day? Keep questioning, keep learning, and I'll catch you in the next explainer.